In the vast expanse of the universe, there are places where the stars fade into distant memories, where galaxies grow so remote they become whispers of light, and where silence prevails in its most profound form. These empty spaces, these cosmic voids that stretch across unimaginable distances, are not truly empty in the scientific sense, but their isolation stirs something deep within us, a quiet wonder that speaks to the very essence of existence itself. Tonight, we embark on a journey unlike any other, a voyage into the deepest, most secluded regions of space, where emptiness reigns supreme and the universe breathes its quiet, infinite breath. We will drift through regions so vast that entire galaxies could be lost within them, like grains of sand in an endless desert. Here, in these cathedral-like expanses of nothingness, time moves differently, and the very concept of distance takes on new meaning. Imagine floating in a place where the nearest star is so far away that its light takes millions of years to reach you, where the familiar constellations of Earth are nowhere to be found, and where the gentle hum of cosmic background radiation is the only reminder that you exist within a living, breathing universe. This is the realm we will explore together, a place where the cosmos reveals its most intimate secrets through the language of silence and space. As we begin this meditative journey, allow yourself to release the boundaries of everyday experience. Here, in the emptiness between worlds, between galaxies, between the very fabric of reality itself, we find not absence, but presence, not void, but fullness of a different kind. The universe, in its infinite wisdom, has created these spaces not as gaps in creation, but as essential breathing room for existence itself. The darkness we will encounter is not the darkness of night on Earth, punctuated by streetlights and the glow of cities. This is the pure, primordial darkness of space, a darkness so complete and so ancient that it predates the birth of stars, the formation of planets, and the emergence of life itself. It is a darkness that holds within it the potential for infinite creation, infinite possibility, infinite wonder. In these quiet moments, as we prepare to venture into the deepest reaches of cosmic emptiness, remember that we are not separate from this vastness. We are part of it, made from the same fundamental particles that dance through these voids, governed by the same forces that shape the large-scale structure of the universe. We are temporary gatherings of stardust, briefly conscious, briefly aware, carrying within us the capacity to contemplate and appreciate the very emptiness from which we emerged and to which we will one day return. So breathe deeply, relax completely, and prepare to immerse yourself in the profound tranquility of deep space, where the universe reveals its most sacred mysteries through the gentle art of emptiness, through the patient wisdom of silence, through the infinite embrace of the cosmic void that connects all things while separating them across the vast theater of existence. To understand the true nature of cosmic emptiness, we must first journey beyond our earthly perspective and embrace a view of the universe that stretches far beyond anything our ancestors could have imagined. When we speak of voids in space, we are not talking about simple empty rooms or hollow containers that we might find in our daily lives. We are describing regions of the universe so vast and so sparsely populated with matter that they challenge our very understanding of what it means for something to exist, what it means for space to be filled or empty, and what it means to contemplate the architecture of creation itself. A cosmic void is fundamentally a large-scale structure in the universe, a region where galaxies are extremely rare or completely absent. These are not small gaps between stars within a single galaxy, not the spaces between planets in our solar system, but enormous expanses that can stretch for hundreds of millions of light years in every conceivable direction. To put this mind-boggling scale in perspective, if our entire Milky Way galaxy, with its 400 billion stars and all its spiral arms and cosmic dust, were reduced to the size of a single grain of sand, some cosmic voids would still be larger than entire football fields, stretching beyond the horizon in all directions. If you were to place our sun at the center of one of these voids, The nearest galaxy might be so incredibly far away that its light would take longer to reach you than the entire history of complex life on Earth. The light from that distant galaxy would have begun its journey before the first fish swam in Earth's oceans, before the first plants colonized the land, before the first animals took their tentative steps onto dry ground. This is the scale of emptiness we are contemplating, a scale that stretches the imagination and humbles our sense of place in the cosmos. These voids form through a process that began shortly after the Big Bang, approximately 13.8 billion years ago, when the universe was still young and hot and the distribution of matter was not perfectly uniform across space. Think of it like cream slowly separating in coffee that has been left to sit undisturbed, or like soap bubbles forming in dishwater, creating thin walls of matter with empty spaces between them. But unlike these familiar examples, the cosmic process unfolds over billions of years and across distances that dwarf entire galaxy clusters. In the early universe, when it was only a few 100,000 years old, slight variations in density, tiny fluctuations in the cosmic soup of matter and energy, caused some regions to contain slightly more matter than others. These variations were incredibly small, perhaps only 1 part in 100,000, but they were enough to set in motion a cosmic dance that would reshape the universe over eons. Over billions of years, gravity worked like an invisible sculptor, and patient artist with infinite time, pulling matter toward the denser regions, and leaving behind these cathedral-like spaces of near emptiness. The formation of cosmic voids is intimately connected to what astronomers call the large-scale structure of the universe. This structure, when viewed from the largest possible perspective, resembles a vast three-dimensional web that spans the entire observable cosmos. Galaxies are arranged along thin filaments that stretch across space like the threads of a cosmic spider web, but a web so large that each thread contains millions of galaxies and stretches across hundreds of millions of light years. Where these cosmic filaments intersect, like the nodes where spiderweb threads come together, we find clusters and superclusters of galaxies, dense neighborhoods, where hundreds or thousands of galaxies gather together in gravitational harmony. These are bustling cosmic cities, regions where galaxy interactions are common, where stars are born at accelerated rates, and where the universe displays its most dramatic and energetic phenomena. But between these filaments, in the spaces bounded by the cosmic web, lie the voids, the quiet spaces where galaxies are few and far between, where the universe whispers instead of shouts. Understanding this cosmic architecture requires us to think in terms of scales that completely dwarf human comprehension. The largest voids we have discovered contain volumes that could comfortably fit thousands of galaxies like our own Milky Way, yet they remain largely empty, populated by perhaps only a few dozen small galaxies scattered across their vast interiors. These regions are not completely devoid of matter, for truly empty space may not exist anywhere in the universe, but the density of galaxies within them is so incredibly low that an observer placed in the center of such a void might see only a handful of distant galaxies scattered across the entire visible sky. Imagine standing in the middle of a vast ocean where the nearest islands are so far away they appear as tiny dots on the horizon, barely visible even on the clearest day. Now multiply that sense of isolation by factors of millions, and you begin to grasp the profound solitude that characterizes these cosmic deserts. An astronaut floating in the center of a cosmic void would see a night sky almost completely black, with perhaps only a few faint smudges of light marking the locations of distant galaxy clusters along the far edges of the void. The discovery of cosmic voids has revolutionized our understanding of how the universe is organized and structured. Before we knew about these vast empty regions, astronomers in the early 20th century assumed that galaxies were distributed more or less randomly throughout space, like stars scattered across the night sky, or like seeds scattered by the wind across a field. The universe was thought to be largely homogeneous on large scales, with matter distributed fairly evenly throughout space. But careful mapping of galaxy positions, conducted over decades by teams of dedicated astronomers using increasingly powerful telescopes and sophisticated instruments, has revealed that the universe has a definite architecture, a clear pattern that emerges only when we step back and observe it from the largest possible scales. This mapping process itself is a testament to human ingenuity, patience, and our deep desire to understand our place in the cosmos. This cosmic cartography requires astronomers to measure the distances to millions of individual galaxies, determining their positions in three-dimensional space with extraordinary precision. Each galaxy represents a single data point in a cosmic census that spans billions of light years and encompasses regions so vast that light from their far edges began its journey toward us when the universe was young. When all these measurements are combined and visualized using powerful computers, the foam-like structure of the universe becomes apparent, with galaxies concentrated along the surfaces of enormous bubbles and vast empty spaces stretching through the interiors. The techniques used to map these structures push the boundaries of observational astronomy. Astronomers must measure not just the brightness of distant galaxies, but also their redshift, the stretching of their light caused by the expansion of the universe. This redshift serves as a cosmic yardstick, allowing astronomers to determine how far away each galaxy lies. The process is painstaking and requires observations of millions of objects, each fainter than the human eye can see, each representing an entire galaxy containing billions of stars. Within these voids, the normal rules of cosmic evolution play out in fascinating and unexpected ways. Without the gravitational influence of nearby galaxies, without the tidal forces and gravitational interactions that shape galaxies in denser regions, the few galaxies that do exist in void regions often evolve in splendid isolation. They may be smaller and less massive than their counterparts in denser regions of the universe, like stunted trees growing in poor soil. They often contain different populations of stars, with some appearing younger and bluer than typical galaxies, suggesting that their isolation has somehow allowed them to maintain active star formation for longer periods. These void galaxies are like hermits of the cosmic community, developing their own unique characteristics in the solitude of deep space. Some show signs of recent star formation, their spiral arms glowing with the blue light of young, hot stars. Others appear to have evolved more slowly, as if the lack of cosmic companionship has somehow limited their growth and development. They offer astronomers a unique laboratory for studying how galaxies evolve when left to their own devices, free from the influences that shape galaxies in more crowded cosmic neighborhoods. The emptiness of cosmic voids also has profound effects on the fundamental nature of space and time themselves. In regions where matter is sparse, where the gravitational field is weaker than in denser parts of the universe, time itself flows differently according to Einstein's theory of general relativity. While this effect is incredibly small, measured in fractions of seconds over millions of years, it represents a fundamental connection between the structure of space and the passage of time. It reminds us that even in the most empty regions of the universe, the very fabric of reality is subtly shaped by the presence or absence of matter. These temporal effects extend far beyond mere scientific curiosity. They represent a profound truth about the nature of existence itself, about how matter and energy shape the stage upon which cosmic events unfold. In the densest regions of the universe, where galaxies cluster together in great superclusters, and where supermassive black holes lurk at galactic centers, time moves more slowly relative to the emptier regions. In the vast voids, time flows slightly faster, as if the universe itself is eager to fill in these empty spaces with the passage of moments and the unfolding of cosmic events. The study of cosmic voids also reveals important clues about the mysterious components of our universe that we cannot directly observe. Dark matter, the invisible substance that makes up approximately 27% of all matter and energy in the cosmos, plays a crucial role in shaping these empty regions. Computer simulations, running on the most powerful supercomputers available to science, show that the distribution of dark matter creates an invisible scaffolding upon which normal matter can collect, forming the filaments and nodes we observe with our telescopes. The voids represent regions where even dark matter is relatively sparse, creating spaces that are truly empty by cosmic standards. These simulations suggest that dark matter formed the first structures in the universe, creating a framework of invisible architecture that guided the formation of the first stars and galaxies. The voids are the spaces between this dark matter scaffolding, regions where the invisible foundation of the universe is thinnest. Dark energy, the even more mysterious force that makes up approximately 68% of the universe and drives the accelerated expansion of space itself, may also be intimately connected to these empty regions. Some theories suggest that the properties of dark energy could be different in void regions compared to denser areas, leading to variations in the rate of cosmic expansion across different parts of the universe. If these theories prove correct, it would mean that the voids are not just empty spaces, but active laboratories, where the fundamental forces of nature express themselves in unique and revealing ways. As we contemplate these vast, empty spaces, stretching across hundreds of millions of light years, we begin to understand that voids are not simply absent spaces, waiting to be filled by future cosmic evolution. They are active participants in the cosmic story, playing a crucial and irreplaceable role in the evolution and structure of the universe as we know it. They provide the essential breathing room that allows galaxy clusters to form and evolve without interference, and they serve as the quiet stages upon which the grand drama of cosmic evolution unfolds across billions of years. In their emptiness, these voids reveal the hidden architecture of creation itself, the underlying pattern that gives structure and meaning to the distribution of matter and energy throughout the cosmos. They demonstrate that the universe is not a random collection of objects scattered through space, but a carefully orchestrated symphony of matter and emptiness, of presence and absence, of structure and void. The philosophical implications of cosmic voids extend far beyond the realm of astronomy and cosmology. They remind us that emptiness and fullness are not opposite concepts, but complementary aspects of existence, two sides of the same cosmic coin. Just as the spaces between notes give music its rhythm and emotional power, just as the pauses between words give speech its meaning and impact, the voids between galaxies give the universe its large-scale structure and allow the cosmic symphony to unfold across space and time. These empty regions teach us about the value of space itself, about the importance of absence in defining presence, about the role that nothingness plays in giving meaning to something. They remind us that creation involves not just the formation of stars and galaxies and planets, but also the careful arrangement of empty spaces that give those objects room to exist and evolve. Though these spaces may seem empty from our limited human perspective, they form the essential framework that holds the galaxies and the stars in their appointed places, creating the cosmic web that connects all matter across the vastness of space and time, while simultaneously separating it into meaningful structures and patterns that reveal the deepest truths about the nature of existence itself. As we drift deeper into our contemplation of cosmic emptiness, we must now turn our attention to the magnificent structure that gives these voids their meaning and context. The cosmic web stands as perhaps the most breathtaking architectural achievement in the known universe, a vast network of matter and energy that spans the entire observable cosmos and creates the framework within which all galaxies, all stars, and ultimately all life exists. Imagine for a moment that you could step outside the boundaries of space and time itself, gaining a perspective that encompasses the entire universe in a single view. From this impossible vantage point, you would see not the random scattering of galaxies that early astronomers once imagined, but rather an intricate three-dimensional tapestry of cosmic proportions. This is the cosmic web, a structure so vast and so complex that the human mind struggles to comprehend its scale, yet so elegant in its organization that it reveals the fundamental principles governing the evolution of the universe itself. The cosmic web consists of 4 primary components, each playing a crucial role in the grand architecture of space. First are the nodes, dense concentrations of matter where multiple filaments intersect, creating the cosmic equivalent of bustling metropolitan areas. These nodes contain the largest galaxy clusters in the universe, massive collections of hundreds or thousands of galaxies bound together by gravity, surrounded by vast halos of dark matter, and permeated by extremely hot gas that glows with X-ray radiation. The filaments themselves form the highways of the cosmic web, thin streams of galaxies and dark matter that stretch across hundreds of millions of light years, connecting the nodes and creating pathways along which matter flows throughout the universe. These cosmic highways are not empty roads, but rather dense concentrations of galaxies arranged in long chains and sheets, like pearls strung along invisible threads that span the vastness of space. Between the filaments lie the walls, 2-dimensional sheets of galaxies that form the boundaries between different regions of the cosmic web. These walls can extend for hundreds of millions of light years in 2 dimensions, while remaining relatively thin in the third, creating vast cosmic surfaces that separate different volumes of space. Some of these walls are so large that they contain millions of galaxies arranged in patterns that stretch across significant fractions of the observable universe. And finally, surrounded by this network of nodes, filaments, and walls, we find the voids, the vast empty regions that we have already begun to explore. These cosmic bubbles represent the largest structures in the universe, spaces so immense that they dwarf even the largest galaxy clusters, yet so empty that an observer within one might see only a handful of distant galaxies scattered across the entire sky. The formation of this cosmic web traces back to the earliest moments of the universe, when quantum fluctuations in the primordial cosmos created tiny variations in the density of matter and energy. These fluctuations, smaller than subatomic particles yet destined to shape the structure of the entire universe, were stretched to cosmic proportions during a brief period of exponential expansion known as cosmic inflation. This inflationary epoch, lasting perhaps only a fraction of a second, took quantum-scale irregularities and expanded them to sizes larger than galaxies, creating the seeds from which all cosmic structure would eventually grow. In the millions of years following the Big Bang, as the universe cooled and expanded, these density variations began to grow under the influence of gravity. Regions that were even slightly denser than average attracted more matter, becoming progressively denser over time. Meanwhile, regions that were slightly less dense than average lost matter to their denser neighbors, becoming progressively emptier as cosmic evolution proceeded. This process, known as gravitational instability, operated like a cosmic version of the rich getting richer and the poor getting poorer, with dense regions accumulating matter, while sparse regions became increasingly empty. Dark matter played a crucial role in this process, providing the gravitational scaffolding upon which the cosmic web could form. Unlike ordinary matter, which interacts with light and can be heated and pressurized, dark matter responds only to gravity, allowing it to collapse into structures much earlier in cosmic history. The dark matter formed the invisible framework of the cosmic web first, creating potential wells into which ordinary matter could later fall, eventually forming the stars and galaxies we observe today. Computer simulations of cosmic web formation reveal the intricate dance of matter and gravity that shaped the universe over billions of years. These simulations begin with the nearly uniform distribution of matter in the early universe and follow its evolution forward in time, tracking the gravitational interactions of billions of particles as they clump together to form the structures we observe. The results are breathtakingly beautiful, showing the gradual emergence of filaments and nodes from an initially smooth distribution of matter. These simulations reveal that the cosmic web is not a static structure but a dynamic, evolving system. Filaments grow and merge over time, nodes accumulate more matter and become denser, and voids expand as matter continues to flow away from them toward denser regions. The cosmic web we observe today represents a snapshot of this ongoing process, a moment in the billions of years of cosmic evolution that began shortly after the Big Bang and will continue far into the future. The scale of the cosmic web challenges our ability to visualize and comprehend its true magnitude. Individual filaments can stretch for hundreds of millions of light years, distances so vast that light traveling at 300,000 kilometers per second takes hundreds of millions of years to traverse them. If we could somehow shrink the entire observable universe to the size of Earth, individual filaments would still stretch for thousands of kilometers, while the nodes where they intersect would be hundreds of kilometers across. The density contrasts within the cosmic web are equally impressive. The densest regions, at the centers of galaxy clusters within the nodes, can contain thousands of times more matter than the average density of the universe. Meanwhile, the centers of the largest voids contain perhaps 1/10 the average cosmic density, creating a range of matter concentrations that spans several orders of magnitude across the cosmic web. This vast range of densities creates equally vast differences in the environments experienced by galaxies in different parts of the cosmic web. Galaxies residing in dense cluster environments face constant gravitational harassment from their neighbors, with close encounters and mergers reshaping their structure over cosmic time. The hot gas that permeates galaxy clusters can strip away the cold gas reservoirs that fuel star formation, gradually transforming star-forming spiral galaxies into quiescent elliptical systems. In contrast, galaxies living along the filaments of the cosmic web experience a more moderate environment, they have neighbors, but not so many as to create the chaotic conditions found in cluster cores. These galaxies often continue forming stars throughout cosmic history, fed by streams of cold gas that flow along the filaments from the surrounding cosmic web. The filaments themselves serve as cosmic highways, channeling gas and even entire galaxies toward the nodes, where they will eventually join larger structures. The cosmic web also plays a crucial role in determining the observable properties of the universe on the largest scales. The arrangement of galaxies along filaments and within nodes creates the patterns we observe in galaxy surveys, while the vast, empty regions between structures contribute to the overall appearance of the cosmic web when viewed from great distances. The statistical properties of galaxy clustering, the way galaxies are distributed throughout space, directly reflect the underlying structure of the cosmic web and provide important tests of our theories of cosmic evolution. One of the most remarkable aspects of the cosmic web is its universality. Computer simulations show that the same basic web-like structure emerges regardless of the specific details of the initial conditions, as long as gravity is the dominant force shaping cosmic evolution. This suggests that the cosmic web represents a fundamental organizational principle of the universe, a natural consequence of how matter behaves under the influence of gravity over cosmic timescales. The discovery and mapping of the cosmic web represents one of the greatest achievements of modern astronomy. Using powerful telescopes and sophisticated instruments, astronomers have painstakingly measured the positions and distances of millions of galaxies, creating three-dimensional maps that reveal the web-like structure of the universe. These surveys require enormous amounts of observing time and computational resources, but they have revolutionized our understanding of cosmic structure and evolution. The largest of these surveys, such as the Sloan Digital Sky Survey and its successors, have mapped the positions of millions of galaxies across significant fractions of the observable universe. When these galaxy positions are plotted in three-dimensional space, the cosmic web becomes clearly visible, with its filaments, nodes, walls, and voids standing out against the backdrop of space. These maps represent some of the most beautiful and scientifically important images ever created, revealing the hidden architecture of the cosmos in unprecedented detail. Recent technological advances have allowed astronomers to extend these surveys to ever greater distances and fainter galaxy populations. Next-generation telescopes and instruments promise to map the cosmic web in even greater detail, potentially revealing how its structure has evolved over cosmic time and how it connects to the formation of the first stars and galaxies in the early universe. The cosmic web also serves as a laboratory for testing our understanding of fundamental physics. The way matter flows along filaments, the properties of the hot gas within galaxy clusters, and the growth rate of cosmic structure all provide tests of our theories of gravity, dark matter, and dark energy. Discrepancies between observations and theoretical predictions could reveal new physics or force us to revise our understanding of how the universe works. As we contemplate the cosmic web in all its magnificent complexity, we begin to appreciate how the vast empty regions we call voids are not separate from this structure, but integral to it. The voids give the web its three-dimensional character, providing the empty spaces that allow the filaments and nodes to stand out in sharp relief. Without the voids, the cosmic web would collapse into a uniform distribution of matter, losing the intricate structure that makes it so beautiful and scientifically revealing. The cosmic web reminds us that the universe is not just a collection of individual objects scattered through space, but a single, unified system in which every part influences every other part. The formation of galaxies within nodes affects the properties of filaments, which in turn influence the evolution of voids, creating a complex web of cosmic cause and effect that spans the entire observable universe. Through the quiet voids, galaxies stretch across the universe like stars in a web, linked by the invisible threads of dark matter and connected by the flows of gas and energy that stream along the filaments of this grand cosmic architecture. This web represents perhaps the most magnificent structure ever discovered, a testament to the power of gravity to organize matter on the largest possible scales and create beauty from the fundamental laws of physics. In the constellation Boötes, the herdsman, visible in Earth's northern sky during spring and summer months, lies one of the most extraordinary discoveries in the history of astronomy. Here, hidden behind the familiar stars that ancient civilizations used to navigate their world, stretches a region of space so vast and so empty that it challenges our understanding of how the universe could have evolved to create such an immense absence of matter. This is the Boötes Void, sometimes called the Great Nothing, a cosmic cavern so large that it could contain thousands of galaxies like our own Milky Way, yet remains almost completely empty of the bright stellar cities that populate most other regions of the universe. The discovery of the Boötes Void reads like a detective story of cosmic proportions, beginning in the 1970s when astronomers first began creating detailed maps of galaxy distributions across the sky. As they painstakingly measured the distances to thousands of galaxies using the most advanced telescopes of their time, a strange pattern began to emerge. In the direction of the constellation Boötes, there appeared to be far fewer galaxies than statistical models predicted should exist in that region of space. At first, astronomers suspected that their observations might be flawed, that perhaps dust clouds within our own galaxy were blocking their view of more distant galaxies, creating an artificial appearance of emptiness, where galaxies actually existed but remained hidden from view. This possibility seemed reasonable, as our own Milky Way galaxy does indeed contain vast clouds of dust that can obscure our view of more distant objects, creating what astronomers call zones of avoidance, where observations become difficult or impossible. However, as more sophisticated instruments became available and observation techniques improved, it became clear that the apparent emptiness in Boötes was not an observational artifact, but a genuine feature of the cosmic landscape. By the 1980s, detailed surveys had confirmed the existence of an enormous void in this region, a cosmic bubble of emptiness that dwarfed anything previously discovered in the universe. The Boötes Void stretches approximately 330 million light-years across at its widest point, making it roughly spherical in shape, though with irregular boundaries that reflect the complex gravitational processes that shaped its formation. To put this staggering size in perspective, if our entire local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller companion galaxies, were placed at the center of the Boötes Void, the nearest edge of the void would still be more than 150 million light-years away in every direction. The emptiness of the Boötes Void is almost as remarkable as its size. Throughout this vast region, astronomers have identified fewer than 60 galaxies, most of them small dwarf systems that pale in comparison to major spiral and elliptical galaxies found in denser regions of the universe. This represents a galaxy density approximately 1/10 that of typical regions of space, creating an environment of cosmic isolation that is difficult to comprehend from our perspective within the relatively dense local group. If an observer were somehow transported to the center of the Boötes Void and looked up at the night sky, they would see perhaps the loneliest view in the universe. Instead of the rich tapestry of stars and galaxies that we observe from Earth, they would see an almost completely black sky, with only a few faint smudges of light marking the locations of the nearest galaxies scattered along the distant edges of the void. The familiar constellations that have guided human navigation and inspired countless stories would be completely absent, replaced by a darkness so profound that it would challenge the very concept of direction and location in space. The few galaxies that do exist within the Boötes Void display characteristics that reflect their isolated environment. Many appear to be younger and more actively star-forming than galaxies in denser regions, suggesting that their isolation from larger cosmic structures has allowed them to retain more of their original gas supplies and continue forming new stars over longer periods of cosmic time. These void galaxies are like cosmic hermits, evolving in splendid isolation without the gravitational harassment and gas stripping that affect galaxies in more crowded environments. Some of the void galaxies show unusual morphologies, with irregular shapes and asymmetric features that may result from their undisturbed evolution. Without the constant gravitational interactions that tend to smooth out irregularities in galaxies living in denser environments, void galaxies can maintain unusual structures and continue forming stars in patterns that might be disrupted in more typical cosmic neighborhoods. The formation of the Boötes Void represents one of the most extreme examples of cosmic evolution, requiring special conditions in the early universe to create such a vast empty region. Computer simulations suggest that voids of this size form when multiple smaller voids merge together over billions of years, gradually expanding and joining to create increasingly larger empty regions. The process begins with small, underdense regions in the early universe that lose matter to surrounding denser areas through gravitational attraction. Over cosmic time, these initially modest underdensities grow larger as matter continues to flow away from them toward regions that will eventually become the filaments and nodes of the cosmic web. The expansion of the universe itself accelerates this process, stretching the empty regions and making them even larger. Eventually, neighboring voids can merge together, creating supervoids like the Boötes void that represent the culmination of billions of years of cosmic evolution. The discovery of the Boötes void had profound implications for our understanding of cosmic structure formation. Voids of this size push the boundaries of what standard cosmological models predict should be possible, given the age of the universe and the strength of gravitational forces. Creating such a large empty region requires either special initial conditions in the early universe or mechanisms for void growth that operate more efficiently than simple gravitational expansion. Some astronomers have suggested that the Boötes void might represent evidence for alternative theories of cosmic evolution, perhaps indicating that the universe underwent different phases of expansion, or that additional forces beyond gravity and dark energy played roles in shaping cosmic structure. Others argue that the void, while exceptional, falls within the range of what current models predict should occasionally occur in a universe as large as ours. The study of the Boötes void has also provided important insights into the nature of dark matter and dark energy, the mysterious components that make up most of the universe. The way matter flows out of voids and the rate at which they expand depends critically on the properties of these invisible constituents. By measuring the size, shape, and galaxy content of voids like Boötes, astronomers can test theoretical predictions about dark matter behavior and dark energy effects. Recent observations using advanced telescopes and instruments have revealed additional details about the structure and contents of the Boötes void. Surveys conducted at different wavelengths of light have confirmed that the void is genuinely empty of normal galaxies, not just hidden by dust or observational limitations. Radio telescopes have detected faint emissions from some of the void galaxies, revealing ongoing star formation processes despite their isolated environment. The Boötes void also serves as a natural laboratory for studying how galaxies evolve in low-density environments. By comparing the properties of void galaxies with those in denser regions, astronomers can isolate the effects of environment on galaxy formation and evolution. This research has revealed that galaxy properties depend strongly on their cosmic neighborhood, with void galaxies showing distinctly different characteristics from their counterparts in clusters and filaments. Modern cosmological surveys continue to map the detailed structure of the Boötes void and search for similar features elsewhere in the universe. These efforts have revealed that while the Boötes void is exceptional in its size and emptiness, it is not unique. Several other large voids have been discovered in different parts of the sky, suggesting that such features, while rare, are natural consequences of cosmic evolution operating over billions of years. The existence of the Boötes void raises intriguing questions about the ultimate fate of cosmic structure. As the universe continues to expand and dark energy drives galaxies apart, will existing voids grow even larger, eventually merging to create even more immense empty regions? Some models predict that the universe will become increasingly void, dominated over cosmic time, with most matter concentrated into ever denser nodes, separated by ever larger expanses of emptiness. The philosophical implications of the Boötes void extend beyond astronomy into questions about the nature of existence itself. This vast empty region reminds us that the universe contains spaces so large and so empty that they challenge human imagination. The void represents a kind of cosmic meditation on the concept of nothingness, a region where the normal markers of space and time become almost meaningless due to the absence of familiar reference points. For an observer within the Boötes void, the usual cosmic signposts that help define location and direction would be largely absent. The concept of nearby and distant would take on new meanings when the nearest significant galaxy might be tens of millions of light-years away. Such an environment would force a complete reconceptualization of what it means to exist within the universe, highlighting our own cosmic circumstances as inhabitants of a relatively dense region filled with billions of neighboring stars. The Boötes void also serves as a reminder of the incredible diversity of environments that exist within the universe. While we are accustomed to thinking about planets, stars, and galaxies as the primary components of the cosmos, voids like Boötes demonstrate that emptiness itself is equally fundamental to cosmic architecture. These vast empty regions are not simply gaps waiting to be filled, but essential components of the cosmic web that give structure and meaning to the distribution of matter throughout space. As we contemplate the immense scale and profound emptiness of the Boötes void, we begin to appreciate how such regions contribute to the overall beauty and complexity of cosmic structure. The void provides a cosmic counterpoint to the dense galaxy clusters and active star-forming regions that capture most astronomical attention. In its silence and emptiness, it offers a different kind of cosmic experience, one that emphasizes the power of absence to define and give meaning to presence. In the vastness of the Boötes void, galaxies vanish into the cosmic distance, leaving only the darkness to stretch on infinitely, creating a region of space where the universe reveals its capacity for creating environments of such profound isolation that they redefine our understanding of what it means to exist within the cosmic web. To truly understand the vast empty regions that dominate our universe, we must venture into the realm of the invisible, exploring the mysterious forces and substances that shape cosmic evolution, despite remaining completely hidden from our direct observation. Dark matter and dark energy, these enigmatic components that together comprise approximately 95% of everything that exists, play fundamental roles in creating and maintaining the cosmic voids that stretch across hundreds of millions of light-years of space. Dark matter, despite its name suggesting absence or emptiness, is actually a form of matter that interacts gravitationally with ordinary matter, but remains invisible to all forms of electromagnetic radiation. It neither emits light like stars, nor absorbs light like dust clouds, nor reflects light like planets. Instead, it reveals its presence only through its gravitational effects on visible matter, like an invisible sculptor whose work can be seen only in the clay it shapes, never in the sculptor itself. This invisible component makes up approximately 27% of all matter and energy in the universe, far outweighing the ordinary matter that forms stars, planets, and everything we can directly observe. The ordinary matter that we think of as comprising the universe, the atoms that make up our bodies and our world, accounts for less than 5% of cosmic inventory. The rest belongs to realms that remain largely mysterious despite decades of intensive scientific investigation. The story of dark matter begins in the early universe, when the cosmos was far simpler and more uniform than it appears today. In those ancient times, roughly 380,000 years after the Big Bang, the universe consisted primarily of a hot, dense soup of particles and radiation. Dark matter particles, whatever their true nature might be, were already present in this primordial mixture, distributed almost uniformly throughout space, but with tiny variations in density that would prove crucial for all subsequent cosmic evolution. Unlike ordinary matter, which interacted strongly with the intense radiation that filled the early universe, dark matter remained largely unaffected by these electromagnetic forces. This immunity to radiation pressure allowed dark matter to begin clumping together under its own gravity much earlier than ordinary matter could, creating the first structures in the universe long before the first stars began to shine. As the universe expanded and cooled, dark matter continued to aggregate into increasingly complex structures under the influence of gravity. Computer simulations show that dark matter forms a vast three-dimensional web of filaments and nodes, an invisible scaffolding that extends throughout the universe and provides the gravitational framework upon which all visible structures eventually form. This dark matter web resembles a cosmic skeleton, giving shape and structure to the universe while remaining completely invisible to our instruments. The regions that would eventually become cosmic voids began as areas where dark matter density was slightly lower than average in the early universe. These underdense regions contain perhaps 10 or 20% less dark matter than typical areas, a small difference that would have enormous consequences over cosmic time. As the universe evolved, dark matter in these underdense regions gradually flowed away toward neighboring areas with higher concentrations, following the inexorable pull of gravity. This process of gravitational drainage operated like water flowing downhill, with dark matter particles moving from regions of lower density toward regions of higher density. Over millions and billions of years, the initially modest differences in dark matter concentration grew larger and larger, creating an increasingly pronounced contrast between dense regions that would become galaxy clusters and sparse regions that would become voids. The formation of cosmic voids thus depends critically on the properties of dark matter and how it responds to gravitational forces. If dark matter behaved differently, if it interacted more strongly with ordinary matter, or if it had different gravitational properties, the structure of the universe would be fundamentally altered. The cosmic web of filaments and voids that we observe today represents a direct consequence of dark matter physics operating over cosmic timescales. Dark energy enters this story as an even more mysterious player, a force or field that appears to be causing the expansion of the universe to accelerate rather than slow down as we might expect from the gravitational attraction of matter. Dark energy makes up approximately 68% of the total energy density of the universe, dominating even dark matter in its cosmic significance. Yet its fundamental nature remains one of the greatest unsolved problems in physics. The discovery of dark energy came as a complete surprise to astronomers in the late 1990s, when observations of distant supernovae revealed that the expansion of the universe is actually speeding up rather than slowing down. This acceleration requires some form of energy that acts repulsively rather than attractively, pushing space itself apart and causing the distance between galaxies to increase at an ever faster rate. The effects of dark energy on void formation are subtle but profound. As space expands due to dark energy, the distances between structures grow larger, making voids appear to expand even faster than they would through gravitational effects alone. Dark energy essentially stretches the fabric of space itself, carrying galaxies apart and making the empty regions between them grow larger over time. This cosmic stretching affects different scales differently. Within galaxy clusters, where gravitational forces are strong enough to hold structures together against the expansion of space, dark energy has little effect. But in the sparse regions that become voids, where gravitational forces are weak, dark energy dominates the evolution, causing these regions to expand faster than they would under the influence of gravity alone. The interplay between dark matter and dark energy creates a complex cosmic dance that shapes the evolution of voids over billions of years. In the early universe, when matter density was higher and dark energy effects were weaker, gravitational processes dominated void formation. Dark matter flowed out of under-dense regions, creating increasingly empty spaces surrounded by increasingly dense walls and filaments. As the universe aged and expanded, dark energy became progressively more important relative to matter. Today, dark energy dominates the cosmic energy budget, and its effects on void expansion have become significant. Current voids are not only growing through the continued outflow of matter, but are also being stretched by the accelerating expansion of space itself. This evolution has important implications for the future of cosmic structure. As dark energy continues to dominate cosmic evolution, voids will grow larger and larger, eventually encompassing most of the volume of the universe. Galaxies will become increasingly isolated as the distances between them grow, creating a cosmos dominated by vast empty regions with matter concentrated into ever more distant islands of stars and gas. The study of void properties provides one of the best ways to probe the nature of dark energy and test different theories about its behavior. The rate at which voids expand, their shapes and sizes, and the way galaxies move within them all depend on the specific properties of dark energy and how it affects the expansion of space. Some theories suggest that dark energy might not be constant throughout space and time, but could vary in density or strength depending on local conditions. If this is true, the properties of dark energy within voids might differ from those in denser regions, leading to observable differences in void evolution that could reveal new physics beyond our current understanding. Other theories propose that dark energy is not a fundamental field or force, but rather an emergent property of space-time itself, arising from quantum mechanical effects that become important only on the largest cosmic scales. These theories make specific predictions about how voids should evolve and what signatures might be detectable through careful observations of void properties. The distribution of dark matter within and around voids also provides important clues about the nature of this invisible component. While voids appear empty of galaxies, they are not necessarily empty of dark matter. Simulations suggest that voids should contain dark matter at densities, perhaps 10 to 20% of the cosmic average, creating a tenuous web of invisible material that pervades even the emptiest regions of space. This residual dark matter within voids might be detectable through its gravitational effects on the few galaxies that do exist in these regions. The motions of void galaxies, their clustering properties, and the way they respond to the large-scale gravitational field all depend on the amount and distribution of dark matter within voids. Recent observations have begun to probe these effects, measuring the velocities of galaxies within voids and comparing them to theoretical predictions. These studies suggest that voids do indeed contain significant amounts of dark matter, consistent with simulations of structure formation in a universe dominated by dark matter and dark energy. The temperature and properties of any gas within voids also depend on dark matter and dark energy effects. Computer simulations predict that voids should contain extremely hot, tenuous gas heated by gravitational processes as matter flows out of under-dense regions. This gas should be so hot and sparse that it emits very little radiation, making it extremely difficult to detect with current instruments. Future observations using more sensitive telescopes and new detection techniques may eventually reveal this hidden component of void contents, providing additional tests of our understanding of dark matter and dark energy physics. The detection of hot gas within voids would confirm theoretical predictions and provide new ways to study the invisible components that dominate cosmic evolution. The quantum nature of dark energy, if it indeed arises from quantum mechanical effects, could also manifest itself in void properties. Some theories predict that quantum fluctuations in dark energy fields could create small-scale variations in the rate of cosmic expansion, leading to subtle irregularities in void shapes and evolution that might be detectable through precision measurements. These quantum effects represent a fascinating connection between the largest structures in the universe and the smallest scales of physical reality. The same quantum mechanical principles that govern the behavior of atoms and subatomic particles might also influence the evolution of cosmic voids spanning hundreds of millions of light years, creating a deep unity between the microscopic and macroscopic realms of existence. As our understanding of dark matter and dark energy continues to evolve through new observations and theoretical developments, cosmic voids will likely play an increasingly important role as laboratories for testing fundamental physics. The extreme conditions within voids, where matter densities are low and dark energy effects are pronounced, provide unique environments for studying these mysterious components of the universe. The formation and evolution of cosmic voids thus represents a cosmic collaboration between visible and invisible components, between matter and energy, between gravitational attraction and cosmic repulsion. Dark matter provides the invisible scaffolding that gives structure to the universe, while dark energy provides the cosmic force that stretches and expands the spaces between structures. What we cannot see is indeed shaping what we can observe. The forces of the unseen are constantly at work, guiding the formation of the universe's vast emptiness and determining the ultimate fate of cosmic structure. In the quiet darkness of cosmic voids, dark matter and dark energy continue their ancient dance, creating and maintaining the largest empty spaces in the universe while remaining forever hidden from our direct perception, visible only through their profound effects on the cosmic web that connects and separates all matter across the vastness of space and time. Imagine for a moment that you could somehow transcend the limitations of human biology and technology, becoming a cosmic traveler capable of journeying across the vast distances that separate galaxies and traversing the enormous empty regions that dominate our universe. What would it feel like to travel through these voids, these cathedral-like spaces where galaxies become distant memories and the familiar signposts of cosmic navigation fade into nothingness? This is perhaps the most profound journey of solitude that could ever be undertaken, a voyage into emptiness that would redefine every concept of space, time, distance, and isolation. Your journey would begin at the edge of a cosmic void, perhaps starting from a galaxy cluster where thousands of stellar cities shine brightly against the cosmic darkness. Behind you, the night sky would blaze with the light of countless galaxies, their spiral arms and elliptical halos, creating a tapestry of cosmic architecture that speaks to billions of years of gravitational sculpture and stellar evolution. The familiar chaos of a dense cosmic neighborhood would surround you, with galaxy interactions, star formation, and the constant dance of gravitational forces creating a dynamic, ever-changing environment. But as you begin your journey into the void, this familiar cosmic landscape would gradually transform in ways that challenge human comprehension. The galaxy cluster behind you would slowly fade from brilliant prominence to a distant glow, its individual members becoming harder and harder to distinguish as cosmic distance increases. The bright foreground galaxies that initially dominated your view would become background objects, then distant lights, then barely perceptible smudges against the cosmic darkness. As you travel deeper into the void, perhaps covering distances of tens of millions of light years, a profound transformation would occur in your cosmic environment. The density of galaxies around you would drop dramatically, from the thousands that populate galaxy clusters to perhaps a few dozen scattered across your entire field of view. These remaining galaxies would appear increasingly isolated, like distant lighthouses in an ocean of darkness, each one separated from its neighbors by distances that dwarf the spaces between galaxies in more typical cosmic regions. The psychological impact of this journey would be unlike anything experienced by conscious beings in our dense cosmic neighborhood. Humans have evolved in an environment rich with reference points, where the horizon provides boundaries, where the sun and moon mark the passage of time, and where stars create familiar patterns that have guided navigation and inspired stories for thousands of years. But in the depths of a cosmic void, these familiar markers of location and direction would gradually disappear, replaced by an emptiness so profound that it would challenge the very concepts of here and there, near and far. After traveling perhaps 50 million light years into the void, you would encounter a cosmic environment unlike anything that exists in the denser regions of the universe. The few remaining galaxies visible in your cosmic horizon would appear as faint, distant objects, their light taking tens of millions of years to reach you across the intervening emptiness. Some of these galaxies might be small dwarf systems, the cosmic hermits that have evolved in isolation within the void. Others might be larger spiral or elliptical galaxies that somehow found themselves trapped within this vast empty region, possibly the remnants of galaxy groups that were torn apart by the expansion of the void over cosmic time. The night sky from this vantage point would present a view of such profound loneliness that it would fundamentally alter any traveler's relationship with the universe. Instead of the rich star fields and bright galactic neighbors that characterize the view from Earth, you would see an almost completely black sky, punctuated by only a handful of extremely faint light sources. The Milky Way, Andromeda, and all the other familiar galaxies of our local group would be invisible, lost in the cosmic distance behind you. Even the most powerful galaxy clusters would appear as barely detectable smudges of light, scattered along the far edges of your cosmic horizon. But this apparent emptiness would not represent true nothingness. Even in the deepest parts of cosmic voids, space itself would contain traces of matter and energy that reveal the subtle complexity of seemingly empty regions. Extremely tenuous gas, perhaps heated to millions of degrees by gravitational processes, would pervade the void at densities billions of times lower than the best vacuum achievable in terrestrial laboratories. This gas would be so sparse that you might travel for millions of kilometers without encountering a single atom, yet its presence would connect your location to the broader cosmic web that extends throughout the universe. The dark matter that helped shape the void would also surround you, invisible but present at perhaps 10 to 20% of its average cosmic density. This ghostly component would create a tenuous gravitational field that subtly influences the motions of the few galaxies visible in the distance, providing a hidden scaffolding that connects even the emptiest regions of space to the larger cosmic architecture. The expansion of the universe itself would become more noticeable during your journey through the void. In dense regions where gravitational forces are strong, the expansion of space has little effect on local structures, which remain bound together by their mutual gravitational attraction. But in the sparse environment of a cosmic void, where gravitational forces are weak, the expansion of space would become apparent as you observe the few distant galaxies slowly receding from your position and from each other. This cosmic expansion would create a sense that the universe is actively stretching around you, making the already vast distances to neighboring structures grow even larger over time. If you could somehow remain in the void for millions or billions of years, you would witness the gradual disappearance of even the most distant galaxies as they recede beyond the cosmic horizon, carried away by the relentless expansion of space driven by dark energy. The silence of this cosmic environment would be absolute in ways that transcend earthly experience of quietude. On Earth, even in the most remote locations, sound waves can propagate through air, and various forms of electromagnetic radiation create a constant background of energy and information. But in the vacuum of space, within a cosmic void, no sound waves can propagate, and the electromagnetic radiation from distant sources would be so faint as to be nearly undetectable. This silence would not be simply the absence of familiar sounds, but a more profound quietude that reflects the fundamental nature of space itself. The cosmic microwave background radiation, the afterglow of the Big Bang that pervades all of space, would still be present, but would represent the only significant source of electromagnetic energy in your immediate environment. This ancient light, cooled by billions of years of cosmic expansion, would provide a subtle reminder that even the emptiest regions of space retain connections to the universe's earliest moments. The experience of time itself might feel different in such an environment. Without the familiar rhythms of stellar evolution, galaxy interactions, and active star formation that mark the passage of cosmic time in denser regions, the void would seem almost timeless, a place where cosmic evolution proceeds at its most leisurely pace. The few galaxies visible in the distance would evolve so slowly that their changes would be imperceptible over human lifetimes, creating an environment where the universe seems frozen in a state of peaceful contemplation. Yet beneath this apparent timelessness, profound processes would still be at work. The expansion of the universe would continue to stretch the void, making it larger and emptier over cosmic time. Dark energy would maintain its relentless push, driving space apart, and ensuring that the isolation of void regions becomes ever more complete. The few galaxies within the void would continue their slow evolution, forming new stars and planets in their quiet cosmic neighborhoods, creating islands of complexity and activity within the vast sea of emptiness. Navigation in such an environment would require completely new concepts of direction and location. The familiar coordinate systems that work well in dense cosmic regions, where bright galaxies provide reference points and local galaxy groups define spatial relationships, would become meaningless in the depths of a void. Instead, navigation would depend on extremely subtle indicators, perhaps the slight gravitational effects of distant structures or the minute variations in the cosmic microwave background that reveal the universe's large-scale architecture. The philosophical implications of experiencing such profound cosmic isolation would be equally extraordinary. The journey through a void would provide a unique perspective on humanity's place in the universe, revealing both our cosmic insignificance and our remarkable uniqueness as conscious observers capable of contemplating such vast emptiness. The experience would highlight the preciousness of our dense cosmic neighborhood, where galaxies cluster together and provide the rich environment necessary for the formation of stars, planets, and ultimately life itself. From the heart of a cosmic void, the regions where galaxies cluster together would appear as distant oases of complexity and activity, cosmic cities where the universe expresses its creative potential through the formation of stars and the evolution of galactic structures. The contrast between these active regions and the peaceful emptiness of the void would illuminate the incredible diversity of environments that exist within the universe, from the densest galaxy clusters to the most isolated empty regions. As your journey through the void continues, perhaps reaching distances of 100 million light-years or more from the nearest significant galaxy cluster, you would find yourself in one of the most isolated locations possible within the observable universe. At this point, the few remaining visible galaxies would appear as barely detectable points of light, their individual stars completely invisible, and their internal structures impossible to resolve across such vast distances. In these silent places, time seems to stretch toward infinity, and the cosmos feels at once vast beyond comprehension and intimately close in its emptiness. The journey through a cosmic void would represent perhaps the ultimate meditation on existence itself, an experience of solitude so profound that it would fundamentally alter any traveler's understanding of space, time, and their place within the grand architecture of the universe. Here, in the heart of cosmic emptiness, the universe reveals its capacity for creating environments of such isolation that they redefine the very meaning of being alone in the cosmos. As we contemplate the vast emptiness of cosmic voids that stretch across hundreds of millions of light years, it becomes natural to reflect upon our own cosmic neighborhood and recognize that even here, in what we consider a relatively dense region of the universe, we exist within our own profound island of isolation. Our solar system, despite being located within the disk of a galaxy containing 400 billion stars, represents its own remarkable example of cosmic emptiness, a quiet oasis surrounded by distances so vast that they humble our understanding of space and solitude. The solar system we call home extends far beyond the familiar realm of planets and asteroid belts that capture most of our attention. The gravitational influence of our Sun reaches outward for nearly 2 light years in all directions, creating a sphere of space roughly 4 light years across that defines the boundary of our cosmic neighborhood. Within this enormous volume, which could comfortably contain thousands of objects the size of Earth's orbit, we find only 8 major planets, a handful of dwarf planets, countless smaller asteroids and comets, and vast expanses of nearly empty space that dwarf the solid objects they contain. To appreciate the scale of emptiness within our own solar system, consider that if the Sun were reduced to the size of a basketball sitting at the center of a large city, Earth would be smaller than a grain of sand, located about 26 meters away. Jupiter, the largest planet, would be roughly the size of a marble, positioned over 130 meters from our basketball-sized Sun. The most distant major planet, Neptune, would be a small bead placed nearly a full kilometer away from the solar center. But even these vast spaces between planets represent only the inner regions of our solar system. Far beyond Neptune lies the Kuiper Belt, a region of icy objects and dwarf planets that extends to perhaps twice Neptune's distance from the Sun. Beyond that stretches the scattered disk, where objects follow highly elongated orbits in the cold outer reaches of the solar system. And encompassing everything lies the Oort cloud, a spherical shell of comets that may extend halfway to the nearest star, creating a vast boundary region where our Sun's gravitational influence gradually yields to the galactic environment. Within this enormous volume of space, the actual solid matter represents an almost negligibly small fraction of the total. If we could somehow gather together all the planets, moons, asteroids, comets, and other solid objects in the solar system, they would occupy less than 1/1000th of the total volume within the Sun's gravitational domain. The rest consists of vacuum so perfect that it makes terrestrial laboratory vacuums seem dense by comparison, space so empty that a spacecraft could travel for millions of kilometers without encountering anything larger than microscopic dust particles. The distances between objects in our solar system create their own form of cosmic loneliness. Light from the Sun, traveling at 300,000 kilometers per second, takes over 8 minutes to reach Earth, demonstrating that even this most fundamental connection between our planet and its parent star involves a significant journey across empty space. Light takes over 5 hours to reach the outer planets, and signals from our most distant spacecraft can take nearly a full day to return to Earth, even when traveling at the speed of light. These travel times represent more than mere technical inconveniences for space exploration. They reveal the fundamental isolation that characterizes existence within our solar system, where each world exists as a separate realm, connected to its neighbors only by the invisible threads of gravity and the patient passage of electromagnetic radiation. No sound can travel between the planets. No acoustic communication can bridge the vacuum that separates these worlds, creating a form of isolation that ensures each planet evolves as its own unique experiment in planetary formation and development. The emptiness between solar system objects also means that the view from any one world reveals only the most distant hints of its cosmic companions. From Earth, the other planets appear as points of light in the night sky, their surfaces and atmospheres invisible to the naked eye, despite sharing the same cosmic neighborhood. Even through powerful telescopes, the other worlds of our solar system remain distant and alien, separated by gulfs of space that challenge our ability to think of them as neighboring worlds rather than remote astronomical objects. This isolation becomes even more pronounced when we consider the distances to our nearest stellar neighbors. The closest star to our Sun, Proxima Centauri, lies approximately 4.2 light-years away, a distance so vast that light from this nearby star takes over 4 years to reach us, despite traveling at the ultimate cosmic speed limit. If we could somehow travel at the speed of our fastest spacecraft, a journey to Proxima Centauri would take tens of thousands of years, highlighting the enormous gulf that separates our solar system from even its closest neighbors. To put this interstellar distance in perspective using our earlier scale model, if our Sun is a basketball at the center of a city, the nearest star would be another basketball located in a completely different city, perhaps several hundred kilometers away. The space between these two cosmic cities would be almost completely empty, containing perhaps a few scattered dust particles, but otherwise representing a void so vast and so empty that it defies comprehension. Within our galaxy, the Milky Way, our solar system occupies a relatively quiet region known as the local bubble, a cavity in the interstellar medium created by ancient supernova explosions that swept gas and dust away from our cosmic neighborhood. This bubble extends for several hundred light-years in all directions, creating a region of space that is emptier than average, even by galactic standards. We exist within a void, isolated not only from other star systems but even from much of the gas and dust that fills the space between stars in denser regions of the galaxy. The local bubble represents our own version of a cosmic void, though on a much smaller scale than the vast empty regions that separate galaxy clusters. Within this bubble, stellar densities are lower than average, and the interstellar medium is thinner and hotter than typical galactic environments. This cosmic emptiness around our solar system may have played important roles in Earth's evolution, reducing the flux of cosmic radiation and providing a relatively stable environment for the development of life over billions of years. The isolation of our solar system becomes even more apparent when we consider the vast scales of galactic rotation. Our entire solar system orbits the center of the Milky Way galaxy at a speed of approximately 220 kilometers per second, yet this enormous velocity carries us through such vast distances that a complete galactic orbit takes roughly 225 million years. During Earth's entire history, our solar system has completed only about 20 orbits around the galactic center, emphasizing the enormous scales involved in galactic structure and the profound isolation that characterizes existence within the cosmic web. This galactic perspective reveals that our solar system, while embedded within a galaxy containing hundreds of billions of stars, remains fundamentally isolated by the vast distances that separate stellar systems. The nearest star-forming regions, where new solar systems are currently being born, lie hundreds of light-years away. The nearest dense star clusters, where stellar neighbors are close enough for significant gravitational interactions, are thousands of light-years distant. We exist in a quiet suburban region of the galaxy, far from the bustling galactic center and the active star-forming regions where cosmic evolution proceeds at a more rapid pace. The emptiness of our cosmic neighborhood also affects our perspective on the universe beyond our galaxy. The vast majority of the universe remains invisible to us, not because of distance alone, but because the space between our solar system and distant objects is so empty that very little matter exists to interact with light traveling across cosmic distances. The darkness of the night sky reflects not only the finite age and size of the universe, but also the fundamental emptiness that characterizes most of cosmic space. From our isolated vantage point within the solar system, we observe the universe through what amounts to a cosmic window, our view shaped by the particular location we occupy within the vast emptiness of space. The galaxies we see in the distance, the cosmic structures we map with our telescopes, and the radiation we detect from the early universe all reach us across enormous expanses of virtually empty space that could contain countless other worlds, yet remain essentially vacant. This cosmic isolation has profound implications for our understanding of life in the universe and our place within cosmic evolution. The vast distances that separate planetary systems mean that any life that evolves elsewhere in the galaxy develops in complete isolation from terrestrial influences, creating the possibility for countless independent experiments in biological evolution occurring simultaneously across the cosmos, yet remaining forever unknown to each other unless civilizations develop technologies capable of bridging interstellar distances. The silence and emptiness that characterize our cosmic neighborhood also create an environment of profound peace and stability that may be essential for the development of complex life. The absence of nearby stellar neighbors means that our solar system remains gravitationally stable over billions of years, allowing planetary orbits to remain nearly constant and providing the long-term environmental stability necessary for biological evolution. The emptiness of space around us shields us from many forms of cosmic interference while providing a clear view of the universe beyond. As we reflect on the isolated nature of our solar system, we begin to appreciate how this emptiness connects us to the larger cosmic voids that dominate universal structure. Our solar system represents a microcosm of cosmic isolation, a small-scale example of how emptiness and solitude characterize existence at every level of cosmic organization, from the spaces between planets to the vast voids between galaxy clusters. Our solar system is indeed an island in the ocean of space, surrounded by emptiness for light years in every direction, connected to the rest of the universe only by gravity, electromagnetic radiation, and the shared heritage of cosmic evolution that links all matter across the vastness of space and time. In this isolation, we find both solitude and connection, both the profound silence of cosmic emptiness and the subtle communications that link our small world to the grand architecture of the universe itself. As we contemplate the vast emptiness of cosmic voids that stretch across hundreds of millions of light years, it becomes natural to reflect upon our own cosmic neighborhood and recognize that even here, in what we consider a relatively dense region of the universe, we exist within our own profound island of isolation. Our solar system, despite being located within the disk of a galaxy containing 400 billion stars, represents its own remarkable example of cosmic emptiness, a quiet oasis surrounded by distances so vast that they humble our understanding of space and solitude. The solar system we call home extends far beyond the familiar realm of planets and asteroid belts that capture most of our attention. The gravitational influence of our Sun reaches outward for nearly 2 light years in all directions, creating a sphere of space roughly 4 light years across that defines the boundary of our cosmic neighborhood. Within this enormous volume, which could comfortably contain thousands of objects the size of Earth's orbit, we find only 8 major planets, a handful of dwarf planets, countless smaller asteroids and comets, and vast expanses of nearly empty space that dwarf the solid objects they contain. To appreciate the scale of emptiness within our own solar system, consider that if the Sun were reduced to the size of a basketball sitting at the center of a large city, Earth would be smaller than a grain of sand, located about 26 meters away. Jupiter, the largest planet, would be roughly the size of a marble, positioned over 130 meters from our basketball-sized Sun. The most distant major planet, Neptune, would be a small bead placed nearly a full kilometer away from the solar center. But even these vast spaces between planets represent only the inner regions of our solar system. Far beyond Neptune lies the Kuiper Belt, a region of icy objects and dwarf planets that extends to perhaps twice Neptune's distance from the Sun. Beyond that stretches the scattered disk, where objects follow highly elongated orbits in the cold outer reaches of the solar system. And encompassing everything lies the Oort cloud, a spherical shell of comets that may extend halfway to the nearest star, creating a vast boundary region where our Sun's gravitational influence gradually yields to the galactic environment. Within this enormous volume of space, the actual solid matter represents an almost negligibly small fraction of the total. If we could somehow gather together all the planets, moons, asteroids, comets, and other solid objects in the solar system, they would occupy less than 1/billionth of the total volume within the Sun's gravitational domain. The rest consists of vacuum so perfect that it makes terrestrial laboratory vacuums seem dense by comparison, space so empty that a spacecraft could travel for millions of kilometers without encountering anything larger than microscopic dust particles. The distances between objects in our solar system create their own form of cosmic loneliness. Light from the Sun, traveling at 300,000 kilometers per second, takes over 8 minutes to reach Earth, demonstrating that even this most fundamental connection between our planet and its parent star involves a significant journey across empty space. Light takes over 5 hours to reach the outer planets, and signals from our most distant spacecraft can take nearly a full day to return to Earth, even when traveling at the speed of light. These travel times represent more than mere technical inconveniences for space exploration. They reveal the fundamental isolation that characterizes existence within our solar system, where each world exists as a separate realm, connected to its neighbors only by the invisible threads of gravity and the patient passage of electromagnetic radiation. No sound can travel between the planets. No acoustic communication can bridge the vacuum that separates these worlds, creating a form of isolation that ensures each planet evolves as its own unique experiment in planetary formation and development. The emptiness between solar system objects also means that the view from any one world reveals only the most distant hints of its cosmic companions. From Earth, the other planets appear as points of light in the night sky, their surfaces and atmospheres invisible to the naked eye, despite sharing the same cosmic neighborhood. Even through powerful telescopes, the other worlds of our solar system remain distant and alien, separated by gulfs of space that challenge our ability to think of them as neighboring worlds rather than remote astronomical objects. This isolation becomes even more pronounced when we consider the distances to our nearest stellar neighbors. The closest star to our Sun, Proxima Centauri, lies approximately 4.2 light-years away, a distance so vast that light from this nearby star takes over 4 years to reach us, despite traveling at the ultimate cosmic speed limit. If we could somehow travel at the speed of our fastest spacecraft, a journey to Proxima Centauri would take tens of thousands of years, highlighting the enormous gulf that separates our solar system from even its closest neighbors. To put this interstellar distance in perspective using our earlier scale model, if our Sun is a basketball at the center of a city, the nearest star would be another basketball located in a completely different city, perhaps several hundred kilometers away. The space between these two cosmic cities would be almost completely empty, containing perhaps a few scattered dust particles, but otherwise representing a void so vast and so empty that it defies comprehension. Within our galaxy, the Milky Way, our solar system occupies a relatively quiet region known as the local bubble, a cavity in the interstellar medium created by ancient supernova explosions that swept gas and dust away from our cosmic neighborhood. This bubble extends for several hundred light-years in all directions, creating a region of space that is emptier than average, even by galactic standards. We exist within a void, isolated not only from other star systems but even from much of the gas and dust that fills the space between stars in denser regions of the galaxy. The local bubble represents our own version of a cosmic void, though on a much smaller scale than the vast empty regions that separate galaxy clusters. Within this bubble, stellar densities are lower than average, and the interstellar medium is thinner and hotter than typical galactic environments. This cosmic emptiness around our solar system may have played important roles in Earth's evolution, reducing the flux of cosmic radiation and providing a relatively stable environment for the development of life over billions of years. The isolation of our solar system becomes even more apparent when we consider the vast scales of galactic rotation. Our entire solar system orbits the center of the Milky Way galaxy at a speed of approximately 220 kilometers per second. Yet this enormous velocity carries us through such vast distances that a complete galactic orbit takes roughly 225 million years. During Earth's entire history, our solar system has completed only about 20 orbits around the galactic center, emphasizing the enormous scales involved in galactic structure and the profound isolation that characterizes existence within the cosmic web. This galactic perspective reveals that our solar system, while embedded within a galaxy containing hundreds of billions of stars, remains fundamentally isolated by the vast distances that separate stellar systems. The nearest star-forming regions, where new solar systems are currently being born, lie hundreds of light-years away. The nearest dense star clusters, where stellar neighbors are close enough for significant gravitational interactions, are thousands of light-years distant. We exist in a quiet suburban region of the galaxy, far from the bustling galactic center and the active star-forming regions where cosmic evolution proceeds at a more rapid pace. The emptiness of our cosmic neighborhood also affects our perspective on the universe beyond our galaxy. The vast majority of the universe remains invisible to us, not because of distance alone, but because the space between our solar system and distant objects is so empty that very little matter exists to interact with light traveling across cosmic distances. The darkness of the night sky reflects not only the finite age and size of the universe, but also the fundamental emptiness that characterizes most of cosmic space. From our isolated vantage point within the solar system, we observe the universe through what amounts to a cosmic window, our view shaped by the particular location we occupy within the vast emptiness of space. The galaxies we see in the distance, the cosmic structures we map with our telescopes, and the radiation we detect from the early universe all reach us across enormous expanses of virtually empty space that could contain countless other worlds, yet remain essentially vacant. This cosmic isolation has profound implications for our understanding of life in the universe and our place within cosmic evolution. The vast distances that separate planetary systems mean that any life that evolves elsewhere in the galaxy develops in complete isolation from terrestrial influences, creating the possibility for countless independent experiments in biological evolution occurring simultaneously across the cosmos, yet remaining forever unknown to each other unless civilizations develop technologies capable of bridging interstellar distances. The silence and emptiness that characterize our cosmic neighborhood also create an environment of profound peace and stability that may be essential for the development of complex life. The absence of nearby stellar neighbors means that our solar system remains gravitationally stable over billions of years, allowing planetary orbits to remain nearly constant and providing the long-term environmental stability necessary for biological evolution. The emptiness of space around us shields us from many forms of cosmic interference while providing a clear view of the universe beyond. As we reflect on the isolated nature of our solar system, we begin to appreciate how this emptiness connects us to the larger cosmic voids that dominate universal structure. Our solar system represents a microcosm of cosmic isolation, a small-scale example of how emptiness and solitude characterize existence at every level of cosmic organization, from the spaces between planets to the vast voids between galaxy clusters. Our solar system is indeed an island in the ocean of space, surrounded by emptiness for light years in every direction, connected to the rest of the universe only by gravity, electromagnetic radiation, and the shared heritage of cosmic evolution that links all matter across the vastness of space and time. In this isolation, we find both solitude and connection, both the profound silence of cosmic emptiness and the subtle communications that link our small world to the grand architecture of the universe itself. In the grand theater of cosmic evolution, we are witnessing one of the most profound and mysterious phenomena in all of existence, the relentless expansion of the universe itself, a process that is gradually stretching the fabric of space and time and making the vast empty regions between galaxies grow ever larger and more isolated. This cosmic expansion represents more than simply objects moving apart through space. Instead, it involves the actual growth of space itself, creating new volume where none existed before, and ensuring that the emptiness we observe in cosmic voids will only become more pronounced as the universe ages. The discovery of cosmic expansion ranks among the most revolutionary insights in the history of human understanding, fundamentally altering our perception of the universe, from a static, unchanging cosmos to a dynamic, evolving system that has been growing and changing since its birth nearly 14 billion years ago. This expansion was first observed in the 1920s by astronomers who noticed that distant galaxies appear to be moving away from us, with more distant galaxies receding faster than nearby ones, creating a pattern that could only be explained if the universe itself is expanding uniformly in all directions. But cosmic expansion differs fundamentally from the familiar experience of objects moving through space. When we observe a distant galaxy receding from us, we are not witnessing that galaxy traveling through space like a spacecraft moving away from Earth. Instead, we are observing the growth of space itself between our galaxy and that distant stellar city, a stretching of the cosmic fabric that carries galaxies apart without requiring them to move through space in the conventional sense. This expansion occurs at every scale throughout the universe, but its effects become noticeable only across the largest distances where the cumulative stretching of space adds up to significant changes. Within our solar system, gravitational forces are strong enough to resist cosmic expansion completely, keeping planetary orbits stable despite the growth of space on larger scales. Even within our galaxy, the gravitational binding of stars and gas clouds overwhelms any expansion effects, maintaining galactic structure against the stretching of space. But in the vast empty regions between galaxies, where gravitational forces are weak and matter density is low, cosmic expansion dominates the evolution of space itself. Here, in the cosmic voids that stretch across hundreds of millions of light years, the expansion of the universe becomes the primary force shaping cosmic architecture, gradually making these already enormous empty regions grow larger and more isolated as cosmic time advances. The mechanism driving this expansion remained mysterious for decades after its discovery, leading to various theories about what force could cause the entire universe to grow uniformly in all directions. The breakthrough came with the realization that expansion could be built into the fundamental structure of space and time itself, emerging naturally from Einstein's theory of general relativity when applied to the universe as a whole. According to this understanding, space possesses an inherent tendency to expand unless prevented from doing so by the presence of matter and energy. In the early universe, when matter density was much higher than today, the gravitational effects of this dense matter actually slowed the expansion, causing the growth rate of space to decrease over time. For billions of years, cosmic expansion gradually decelerated as gravity worked against the stretching of space, leading cosmologists to predict that expansion might eventually slow to a stop or even reverse, causing the universe to begin contracting back toward a eventual collapse. However, observations in the late 1990s revealed one of the most surprising discoveries in the history of astronomy. The expansion of the universe is not slowing down but actually accelerating, growing faster now than it was in the past. This acceleration requires the existence of some form of energy that acts repulsively rather than attractively, pushing space apart with ever-increasing strength as the universe grows larger and older. This mysterious component, now known as dark energy, appears to make up approximately 68% of all energy in the universe, yet its fundamental nature remains one of the greatest unsolved problems in physics. Dark energy seems to be a property of space itself, becoming more dominant as the universe expands, and the density of ordinary matter and dark matter decreases through dilution across ever larger volumes. The effects of dark energy are most pronounced in the emptiest regions of the universe, where its repulsive influence faces the least resistance from gravitational forces. In cosmic voids, where matter density is already far below the cosmic average, dark energy drives expansion at rates that gradually overwhelm any remaining gravitational effects, causing these regions to grow faster than simple geometric expansion would predict. This accelerated expansion has profound implications for the evolution of cosmic structure and the future appearance of the universe. As space continues to stretch at an increasing rate, the distances between galaxy clusters grow larger, making cosmic voids expand faster than the matter within them can redistribute. The result is a universe that becomes increasingly dominated by empty space, with matter concentrated into ever more isolated islands, separated by ever larger expanses of vacuum. Computer simulations that model the future evolution of cosmic expansion paint a picture of a universe becoming progressively more empty and isolated over cosmic time. As billions of years pass, the acceleration driven by dark energy will cause currently observable galaxies to recede beyond the cosmic horizon, disappearing from view as the expansion of space carries them away faster than light can travel between them. Eventually, even nearby galaxy clusters will become isolated from each other, surrounded by regions of space that have expanded so much that light from neighboring clusters can no longer bridge the growing distances. Our own local group of galaxies, currently bound together by gravity and destined to merge into a single large galaxy over the next few billion years, will find itself completely alone in an expanding sea of emptiness, with no other galaxies visible anywhere in the sky. This cosmic isolation represents the ultimate triumph of empty space over matter, a future where the vast voids that currently separate galaxy clusters expand to encompass nearly the entire observable universe. The cosmic web of filaments and nodes that currently give structure to the universe will gradually dissolve as expansion stretches the connections between structures beyond their ability to maintain gravitational contact. The expansion of cosmic voids also affects the physical conditions within these already empty regions. As space stretches, any residual matter within voids becomes even more dilute, reducing the already low particle densities to levels that approach absolute vacuum. The tenuous gas that computer simulations predict should exist within voids will be stretched and cooled by expansion, making it even more difficult to detect and study. Similarly, the expansion affects any electromagnetic radiation traveling through voids, stretching the wavelengths of light and radio waves as they cross these growing empty regions. This cosmological redshift provides one of the primary tools astronomers use to measure cosmic expansion, but it also means that radiation from distant sources becomes progressively more difficult to detect as expansion stretches it to longer and longer wavelengths. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, is continuously being stretched by cosmic expansion, gradually cooling as its wavelengths grow longer. This ancient light, which currently has a temperature of about 2.7 degrees above absolute zero, will continue cooling as the universe expands, eventually becoming so stretched and dilute that it provides negligible heating to any matter that might exist in the far future universe. The study of cosmic expansion and its effects on void evolution has also revealed important connections between the largest and smallest scales of physical reality. The dark energy that drives accelerated expansion may be related to quantum mechanical effects operating at subatomic scales, suggesting that the emptiness of cosmic voids is ultimately shaped by processes occurring at the most fundamental levels of physical reality. Some theories propose that dark energy arises from the quantum vacuum itself, emerging from the constant creation and annihilation of virtual particles that quantum mechanics predicts should occur even in completely empty space. If these theories are correct, then the expansion of cosmic voids is directly connected to the strange quantum mechanical properties of vacuum, creating a deep link between cosmic emptiness and the fundamental nature of space and time. Future observations using increasingly powerful telescopes and instruments will continue to probe the expansion of cosmic voids and test our understanding of dark energy and its effects. Surveys that map the positions and velocities of galaxies within and around voids provide crucial data for testing theoretical models of cosmic expansion and constraining the properties of dark energy. These observations may eventually reveal whether dark energy is truly constant throughout space and time, or whether its strength varies in different cosmic environments. Variations in dark energy density could lead to different expansion rates in different regions of the universe, creating a complex pattern of cosmic evolution that goes beyond simple uniform expansion. The expansion of the universe also raises profound philosophical questions about the nature of space, time, and existence itself. The fact that space can grow and stretch challenges our intuitive understanding of what it means for something to expand, forcing us to reconceptualize space, not as a fixed stage upon which cosmic events unfold, but as a dynamic participant in cosmic evolution. As we contemplate the growing emptiness created by cosmic expansion, we witness the universe engaged in a grand transformation that will ultimately reshape the cosmic landscape beyond recognition. The voids that we observe today, already vast beyond comprehension, represent only the beginning of a process that will eventually make emptiness the dominant characteristic of cosmic architecture. Yet this expansion also connects us to the deepest mysteries of existence, linking the growth of cosmic voids to fundamental questions about the nature of space, time, and the forces that govern reality at its most basic level. As the universe stretches, the gaps between galaxies widen, and what seems empty grows ever more immense. We find ourselves witnessing one of the most profound processes in all of cosmic evolution, a transformation that reveals the dynamic nature of existence itself and the inexorable march of cosmic time toward an ever more empty and ever more mysterious future. As we delve deeper into the nature of cosmic emptiness, we encounter one of the most profound and counterintuitive discoveries in modern physics: the realization that even the most empty regions of space, even the vast cosmic voids that stretch across hundreds of millions of light years with barely any matter to be found, are far from truly empty when examined at the smallest possible scales. At the quantum level, where the familiar laws of classical physics give way to the strange and wonderful realm of quantum mechanics, empty space itself becomes a seething ocean of activity, filled with virtual particles that flash into existence and disappear again in timeframes so brief that they challenge our very concepts of existence and nothingness. This quantum nature of empty space represents one of the most beautiful and mysterious aspects of physical reality, revealing that the concept of absolute emptiness may not exist anywhere in the universe. Even in the perfect vacuum of cosmic voids, far from any stars or galaxies, space itself participates in a constant dance of creation and annihilation that operates according to the fundamental principles of quantum uncertainty and the strange rules that govern matter and energy at the smallest possible scales. The discovery of quantum fluctuations in empty space emerged from the development of quantum field theory in the early 20th century, when physicists began to understand that the quantum mechanical description of reality requires us to think about particles not as tiny billiard balls moving through space, but as excitations in underlying fields that permeate all of existence. Every type of particle, from electrons to photons to the exotic particles that mediate fundamental forces, corresponds to waves and vibrations in these quantum fields that extend throughout the universe. According to quantum mechanics, these fields can never be completely still, even in the apparent emptiness of perfect vacuum. The Heisenberg uncertainty principle, one of the foundational concepts of quantum theory, tells us that energy and time cannot both be precisely determined simultaneously, which allows for temporary violations of energy conservation on extremely short timescales. This quantum uncertainty permits the spontaneous creation of particle-antiparticle pairs from the energy fluctuations of empty space itself, provided these virtual particles disappear again quickly enough that their brief existence remains within the bounds allowed by quantum uncertainty. These quantum fluctuations occur everywhere throughout the universe, from the densest cores of stars to the most empty regions of cosmic voids. In the depths of space, far from any ordinary matter, virtual particles continuously pop into existence in pairs, exist for infinitesimally brief moments, and then annihilate each other and disappear back into the quantum vacuum from which they emerged. This process happens countless times every second in every cubic centimeter of space, creating a hidden layer of activity that underlies all of cosmic evolution. The timescales involved in these quantum fluctuations are almost impossible to comprehend from our everyday perspective. Virtual particles typically exist for periods measured in units so small that they make a single second seem like an eternity. A virtual particle pair might exist for only 10 to the power of -23 seconds, a duration so brief that light, traveling at 300,000 kilometers per second, can move only a distance smaller than the nucleus of an atom before the particles vanish again into nothingness. Yet despite their incredibly brief lifetimes, these virtual particles have real and measurable effects on the physical world. They contribute to the masses of ordinary particles, affect the strength of electromagnetic forces, and create subtle but detectable changes in the energy levels of atoms. Laboratory experiments have confirmed the existence of these quantum fluctuations through measurements of the Casimir effect, where metal plates placed extremely close together in vacuum experience a tiny attractive force caused by the quantum fluctuations of empty space between them. The energy associated with quantum fluctuations in empty space has profound implications for our understanding of cosmic evolution and the nature of dark energy that drives the acceleration of universal expansion. Some theoretical calculations suggest that the quantum vacuum should possess an enormous energy density, far greater than the energy density of all ordinary matter and radiation in the universe combined. If this vacuum energy could act gravitationally, it would cause space to expand at rates that would tear apart atoms and prevent the formation of any cosmic structures. The fact that we observe a universe filled with galaxies, stars, and planets, rather than a rapidly expanding empty cosmos, suggests that either the vacuum energy does not contribute to cosmic expansion in the way that naive calculations predict, or that some unknown mechanism cancels out most of the vacuum energy, leaving only a tiny residual amount that we observe as dark energy. This discrepancy between theoretical predictions and observational reality represents one of the most serious unsolved problems in theoretical physics, known as the cosmological constant problem. The resolution of this problem may require fundamental advances in our understanding of quantum mechanics, general relativity, or both. Some theories propose that the vacuum energy is exactly cancelled by other contributions, perhaps through supersymmetry or other symmetry principles that ensure the total vacuum energy remains precisely zero. Other approaches suggest that our current understanding of how quantum mechanics and gravity interact may be fundamentally incomplete, requiring new physics that operates on cosmic scales. Within cosmic voids, where ordinary matter density is extremely low, the effects of quantum fluctuations may become more pronounced relative to the influence of conventional matter and energy. The virtual particles that constantly appear and disappear throughout these empty regions contribute to the overall energy density of space, potentially affecting the rate at which voids expand and evolve over cosmic time. Some theoretical models suggest that quantum fluctuations could create tiny variations in the expansion rate of different regions within cosmic voids, leading to a complex pattern of void evolution that goes beyond the simple uniform expansion predicted by classical cosmology. These quantum effects might be too small to detect with current instruments, but future observations with more sensitive equipment could potentially reveal signatures of quantum mechanical processes operating on cosmic scales. The quantum nature of empty space also raises intriguing questions about the fundamental structure of space and time themselves. If space is filled with quantum fluctuations at the smallest scales, then the smooth, continuous nature of space that we observe on larger scales may be an approximation that breaks down when examined with sufficient precision. At the Planck scale, where quantum effects and gravitational effects become equally important, space and time may have a foamy, discontinuous structure quite different from our everyday experience. This quantum foam, as it is sometimes called, represents a regime where our current theories of physics reach their limits, and new understanding is required. The quantum fluctuations that occur at these scales may be responsible for the initial density variations that eventually grew to become the cosmic web of galaxies and voids that we observe today, connecting the smallest quantum mechanical processes to the largest structures in the universe. The study of quantum fluctuations in cosmic voids also provides a natural laboratory for testing the boundaries between quantum mechanics and general relativity. In these extremely low-density environments, quantum effects that are normally overwhelmed by the presence of ordinary matter may become more apparent, potentially revealing new physics that operates only in the most empty regions of space. Recent theoretical work has suggested that quantum fluctuations might be responsible for generating the initial seeds of cosmic structure during the inflationary period of the early universe. If this is correct, then the galaxies and voids we observe today all trace their origins back to quantum mechanical processes that occurred in the first fraction of a second after the Big Bang, when the entire observable universe was smaller than a subatomic particle. This connection between quantum mechanics and cosmic structure formation represents one of the most beautiful unifications in modern physics, linking the behavior of virtual particles in empty space to the formation of galaxies, stars, and ultimately planets and life itself. The quantum fluctuations that occur in cosmic voids today may be direct descendants of the same processes that created the initial density variations from which all cosmic structure eventually emerged. The implications of quantum mechanics for our understanding of cosmic voids extend beyond purely scientific questions to touch on fundamental philosophical issues about the nature of existence and reality. If empty space is filled with virtual particles that constantly appear and disappear, then the boundary between existence and non-existence becomes blurred in ways that challenge our everyday concepts of what it means for something to be real. Virtual particles exist in a strange quantum limbo, real enough to have measurable effects on the physical world, yet ephemeral enough to violate energy conservation temporarily, without violating the fundamental laws of physics. They represent a form of existence that is neither fully real nor completely imaginary, occupying a middle ground that reflects the strange and wonderful nature of quantum reality. This quantum perspective on cosmic voids reveals that even the most empty regions of space participate in the fundamental creativity of the universe, continuously generating and destroying matter and energy in patterns that may ultimately be responsible for the existence of everything we observe. The apparent emptiness of cosmic voids conceals a hidden richness that operates according to principles that transcend our everyday experience while remaining grounded in the deepest laws of physics. Future experiments and observations may eventually reveal more about the quantum nature of cosmic voids and the role that virtual particles play in cosmic evolution. Space-based instruments that can detect extremely subtle variations in the properties of empty space might be able to measure the effects of quantum fluctuations directly, providing new insights into the connection between quantum mechanics and cosmology. At the smallest scales, the void is indeed alive, with fleeting particles, always shifting, always changing, never truly still, despite appearing empty from our macroscopic perspective. It is emptiness in the conventional sense, devoid of ordinary matter and energy, but it is not stillness in the quantum mechanical sense. Filled instead with a constant dance of creation and annihilation that reveals the deep connection between the quantum world and the cosmic architecture that emerges from quantum processes operating over billions of years and across distances that span the observable universe. As we reach the final chapter of our journey through the vast emptiness of cosmic voids, we must turn our contemplation toward the ultimate questions that these empty regions raise about the fate of the universe itself. What does the future hold for the cosmic web of galaxies and voids that we observe today? Will the accelerating expansion driven by dark energy continue forever, gradually stretching the universe until emptiness dominates everything? Or might other forces and processes intervene to create a different cosmic destiny, one where the current patterns of structure and void might transform into something entirely unexpected? The study of cosmic voids and their evolution provides crucial insights into these profound questions about the ultimate fate of existence itself. By understanding how empty regions grow and change over cosmic time, we can extrapolate forward billions and trillions of years into the future, painting pictures of possible cosmic destinies that reveal the long-term consequences of the forces we observe operating in the universe today. Current observations and theoretical models paint several possible scenarios for the cosmic future, each with dramatically different implications for the role of emptiness in the evolving universe. The scenario that seems most consistent with present evidence is often called the heat death of the universe, a future where cosmic expansion continues to accelerate, driven by dark energy, until the universe becomes a cold, dark, and nearly empty expanse, where isolated islands of matter drift apart in an ever-growing sea of vacuum. In this heat death scenario, the cosmic voids we observe today represent harbingers of the universe's ultimate destiny. As dark energy continues to drive accelerated expansion, the distances between galaxy clusters will grow larger and larger, eventually stretching beyond the cosmic horizon and making neighboring structures disappear from view. Our own local group of galaxies, currently destined to merge into a single large galaxy over the next 5 billion years, will find itself completely alone in an expanding universe, surrounded by empty space that has grown so vast that no other galaxies remain visible anywhere in the sky. The timescales involved in this cosmic evolution stretch far beyond human comprehension. Within the next trillion years, star formation will gradually cease throughout the universe as galaxies exhaust their supplies of gas and dust needed to create new stars. The existing stars will continue to shine for vastly longer periods, with the smallest red dwarf stars potentially burning for hundreds of trillions of years. But eventually, even these long-lived stellar furnaces will exhaust their nuclear fuel and fade into darkness. As star formation ends and existing stars burn out, the universe will enter what cosmologists call the degenerate era, a period lasting from roughly 1 trillion to 10 to the power of 36 years after the Big Bang. During this unimaginably long epoch, the primary sources of energy in the universe will be the gradual decay of protons, the fundamental particles that make up atomic nuclei, and the slow evaporation of black holes through Hawking radiation. Throughout this degenerate era, cosmic voids will continue to expand and grow, driven by the relentless acceleration of dark energy. The already vast empty regions will stretch to encompass nearly the entire volume of the observable universe, with the few remaining stellar remnants, planets, and black holes scattered across distances so enormous that they might as well exist in separate universes, completely isolated from each other by the expansion of space. Yet even this scenario of gradual decay and increasing emptiness may not represent the final chapter in cosmic evolution. Some theoretical models predict an even more dramatic fate known as the Big Rip, where the acceleration of cosmic expansion becomes so extreme that it eventually overcomes all other forces in the universe, tearing apart galaxies, stars, planets, and ultimately even atoms themselves. In the Big Rip scenario, dark energy does not remain constant, but instead grows stronger over time, causing the expansion of space to accelerate at an ever-increasing rate. This runaway expansion would first isolate galaxy clusters from each other, then tear apart individual galaxies, then disrupt stellar systems, and finally overwhelm the electromagnetic forces that hold atoms together, reducing all matter to its most fundamental components, scattered across an rapidly expanding universe. The timescales for the Big Rip depend on the specific properties of dark energy and how it might evolve over cosmic time. Some models suggest this ultimate dissolution could occur within 20 billion years, while others place it in the more distant future. If the Big Rip scenario proves correct, then cosmic voids represent not just growing empty regions, but the future state of all space, with emptiness expanding until it encompasses and destroys every structure in the universe. However, other theoretical possibilities suggest that the universe might follow very different evolutionary paths that could dramatically alter the role of cosmic voids in the far future. Some models propose that dark energy might not remain constant or continue strengthening indefinitely, but could instead weaken or even reverse its effects over extremely long timescales. If dark energy were to weaken significantly, cosmic expansion could slow down and potentially even reverse, leading to a big crunch scenario where the universe begins contracting back toward a hot, dense state similar to the Big Bang. In such a scenario, cosmic voids would gradually shrink as space contracts, bringing distant galaxy clusters back together and eventually merging all matter and energy into a final cosmic singularity. Alternatively, cyclical models of cosmic evolution suggest that the universe might undergo repeated cycles of expansion and contraction, with each cycle lasting hundreds of billions of years. In these models, the current era of accelerating expansion and growing voids would eventually give way to a period of contraction, followed by a new Big Bang that initiates another cycle of cosmic evolution, with new opportunities for structure formation and the creation of new patterns of matter and emptiness. More exotic theoretical possibilities include scenarios involving phase transitions in the fundamental structure of space and time itself. Some theories suggest that our current universe exists in a metastable state that could eventually decay into a lower energy configuration, potentially altering the laws of physics and the nature of cosmic evolution in ways that we cannot currently predict or comprehend. These phase transition scenarios could dramatically alter the evolution of cosmic voids and the distribution of matter throughout the universe. A transition to a new physics regime might cause space itself to behave differently, potentially eliminating dark energy or introducing new forces that could either accelerate void growth or cause empty regions to collapse and fill with new forms of matter and energy. The study of cosmic voids also raises intriguing questions about the possibility of other universes and the broader multiverse that some theoretical models suggest might exist beyond our observable cosmos. If our universe is part of a larger multiverse containing countless other cosmic domains, each with its own laws of physics and evolutionary history, then the fate of our cosmic voids might be just one example among infinite variations of cosmic evolution playing out across the multiverse. Some multiverse theories suggest that new universes could spontaneously emerge from quantum fluctuations in cosmic voids, creating bubble universes that expand and develop their own cosmic structures while remaining causally disconnected from our observable universe. In this scenario, cosmic voids might serve as cosmic wombs where new universes are born, making emptiness not just the future state of our cosmos, but also the source of infinite new cosmic realities. The ultimate fate of cosmic voids also depends on processes that we may not yet understand or have discovered. Physics beyond the standard model of particle physics could introduce new particles, forces, or interactions that significantly alter cosmic evolution over extremely long timescales. Dark matter, which we know exists but do not yet fully understand, might undergo decay processes or phase transitions that could affect the structure and evolution of cosmic voids in unexpected ways. Similarly, our understanding of quantum mechanics and general relativity may prove incomplete when applied to the extreme conditions and vast timescales relevant to cosmic evolution. New physics operating at the intersection of quantum mechanics and cosmology could introduce effects that alter the long-term behavior of cosmic expansion and the evolution of cosmic structure in ways that current theories cannot predict. The development of more powerful observational tools and theoretical frameworks will continue to refine our understanding of cosmic evolution and the ultimate fate of cosmic voids. Future space-based telescopes capable of observing the most distant galaxies will provide direct evidence about how cosmic expansion has changed over the history of the universe, potentially revealing whether dark energy is truly constant or evolving over cosmic time. Advanced computer simulations that model cosmic evolution over unprecedented timescales will help us understand how current cosmic structures might evolve under different scenarios for the future behavior of dark energy and other cosmic forces. These simulations will paint increasingly detailed pictures of possible cosmic futures and the role that emptiness might play in each scenario. The philosophical implications of these cosmic futures extend far beyond scientific speculation to touch on fundamental questions about the nature of existence, consciousness, and meaning in an evolving universe. If the universe is indeed destined to become increasingly empty and cold, what does this mean for the significance of life, intelligence, and the complex structures that have emerged during the current era of cosmic evolution? Some thinkers argue that the temporary nature of cosmic structure makes it even more precious and meaningful, like a beautiful sunset that gains significance partly from its ephemeral character. The fact that galaxies, stars, planets, and life itself exist at all in a universe that may be destined for ultimate emptiness could be seen as a remarkable achievement that gives cosmic evolution its drama and poignancy. Others suggest that intelligent life might find ways to survive and thrive even in the far future universe of increasing emptiness, perhaps by developing technologies that can harness the subtle energy sources that will remain available even after stars have died and conventional energy sources have been exhausted. The vast timescales available for future evolution could allow for forms of intelligence and consciousness that transcend our current biological limitations and find meaning and purpose even in cosmic environments dominated by emptiness. As time moves forward into the cosmic future, the universe will indeed continue to expand, stretching the voids until they become eternal features of cosmic architecture. Whether this expansion continues forever, accelerates into a big rip, reverses into a big crunch, or transforms through currently unknown physics into something entirely different, remains one of the greatest open questions in cosmology. The cosmic voids we observe today offer windows into this ultimate future, revealing the processes and forces that will shape the destiny of all cosmic structure over timescales that dwarf the current age of the universe. In their growing emptiness, we glimpse both the grandeur and the mystery of cosmic evolution, the beautiful complexity that emerges from simple physical laws operating over vast expanses of space and time, and the ultimate questions about existence itself that may never be fully answered, but will continue to inspire wonder and contemplation as long as conscious beings exist to ponder the infinite depths of cosmic mystery. As our journey through the vast emptiness of the universe draws to a close, we find ourselves transformed by the contemplation of cosmic voids, those cathedral-like spaces that stretch across hundreds of millions of light years and remind us of the profound silence that characterizes most of existence. We have traveled together through realms of emptiness so vast that they challenge human comprehension, explored the hidden quantum activity that underlies apparent nothingness, and gazed into possible futures where emptiness may eventually dominate all of cosmic architecture. The emptiness of space, as we have discovered, is not something to fear but something to marvel at, to appreciate, and to understand as an essential component of the cosmic web that gives structure and meaning to the universe itself. These vast empty regions are not gaps waiting to be filled or mistakes in cosmic design, but rather fundamental features of existence that reveal the deepest truths about how gravity, dark matter, dark energy, and the basic forces of nature collaborate to create the magnificent architecture we observe stretching across the cosmos. In the cosmic voids we have explored, we have found not absence but presence of a different kind, not nothingness but a subtle form of fullness that operates according to principles that transcend our everyday experience. The quantum fluctuations that fill even the emptiest regions of space, the dark matter that provides invisible scaffolding for cosmic structure, and the dark energy that drives the acceleration of universal expansion all remind us that emptiness and fullness are not opposites, but complementary aspects of a deeper cosmic reality. Our exploration has revealed that cosmic voids are active participants in the ongoing story of universal evolution, playing crucial roles in shaping the distribution of galaxies, influencing the formation of cosmic structure, and providing natural laboratories where the most fundamental forces of nature express themselves in their purest forms. These regions of cosmic isolation have taught us about the nature of space and time, the behavior of matter and energy under extreme conditions, and the subtle processes that connect the largest structures in the universe to the quantum mechanical realm of virtual particles and uncertainty principles. The silence we have encountered in our journey is not the silence of death or emptiness, but the profound silence of cosmic meditation, a quietude so deep that it allows us to hear the subtle rhythms of universal evolution, the gentle breathing of space itself as it expands and stretches under the influence of dark energy, and the quiet whispers of electromagnetic radiation that carry messages across billions of light-years from distant galaxies and ancient cosmic events. This cosmic silence offers us a unique perspective on our own existence and our place within the grand architecture of space and time. From our vantage point on a small planet, orbiting a typical star in a galaxy containing hundreds of billions of other stars, we are able to perceive and contemplate emptiness on scales that dwarf our local cosmic neighborhood. This ability to transcend our immediate surroundings and appreciate the vast context within which we exist represents one of the most remarkable achievements of human consciousness and scientific inquiry. The cosmic voids we have explored remind us that our own cosmic neighborhood, despite seeming dense and populated with familiar objects, is itself an island of relative complexity surrounded by vast expanses of near emptiness. Our solar system, our galaxy, and our local group of galaxies all exist as temporary gatherings of matter in a universe dominated by empty space, brief concentrations of stars and planets that will eventually disperse as cosmic expansion carries structures apart over billions of years. Yet this temporary nature of cosmic structure does not diminish its significance, but rather enhances our appreciation for the remarkable processes that have created the conditions necessary for the emergence of stars, planets, and ultimately life and consciousness. The cosmic voids that surround and separate galaxy clusters provide the essential breathing room that allows gravitational processes to operate over cosmic timescales, creating the stable environments necessary for stellar evolution, planetary formation, and biological development. Our journey through cosmic emptiness has also revealed the deep connections that link all scales of physical reality, from the quantum fluctuations that occur in empty space to the large-scale structure of the cosmic web that spans the observable universe. The same fundamental forces and principles that govern the behavior of subatomic particles also shape the evolution of cosmic voids, spanning hundreds of millions of light-years, creating a unity of physical law that extends across more than 60 orders of magnitude in scale. This cosmic unity suggests that the emptiness we have explored is not separate from the complex structures that capture most of our attention, but rather represents the foundation upon which all cosmic architecture rests. The voids provide the context that gives meaning to galactic clusters, the silence that makes cosmic noise significant, and the emptiness that allows fullness to be appreciated and understood. As we reflect on the cosmic futures we have contemplated, from scenarios of increasing isolation driven by dark energy to possibilities of universal collapse or transformation through unknown physics, we are reminded that the universe is not a static collection of objects, but a dynamic, evolving system that continues to surprise and challenge our understanding. The cosmic voids we observe today may represent only one phase in a cosmic evolution that could unfold in directions we cannot currently imagine or predict. The philosophical implications of our exploration extend far beyond astronomy and cosmology to touch on fundamental questions about the nature of existence, consciousness, and meaning in a universe dominated by apparent emptiness. The fact that conscious beings like ourselves can emerge from cosmic evolution and develop the capacity to contemplate and appreciate cosmic voids represents a remarkable achievement that gives significance to the entire cosmic story, regardless of what ultimate fate awaits the universe in the distant future. The emptiness of cosmic voids teaches us about the value of silence, solitude, and contemplation in our own lives and consciousness. Just as cosmic voids provide essential breathing room for galactic evolution, periods of quiet reflection and meditation provide essential space for personal growth, understanding, and the development of wisdom. The cosmic perspective gained through contemplating vast empty spaces can help us appreciate the preciousness of complexity, consciousness, and connection, while also finding peace in simplicity, silence, and solitude. Our exploration has shown us that emptiness and fullness, silence and sound, presence and absence are not competing opposites, but complementary aspects of a deeper reality that transcends simple dualistic thinking. The cosmic voids that initially appeared as mere gaps in cosmic structure have revealed themselves as essential components of universal architecture, active participants in cosmic evolution, and profound teachers about the nature of space, time, and existence itself. As we prepare to rest beneath the stars, carrying with us the perspective gained through our journey into cosmic emptiness, we can appreciate how our small planet Earth exists within nested layers of cosmic structure and void, from the emptiness within our own solar system to the vast empty regions that separate galaxy clusters across billions of light years. This cosmic context does not diminish our significance, but rather enhances our appreciation for the remarkable series of events and processes that have led to our existence and our capacity to contemplate the universe that contains us. The cosmic voids we have explored continue their patient expansion, growing larger and emptier as dark energy stretches the fabric of space itself, yet they remain connected to all other cosmic structures through the invisible threads of gravitational influence, electromagnetic radiation, and the shared history of cosmic evolution that links all matter and energy to the primordial conditions of the Big Bang 13.8 billion years ago. In the infinite silence of these cosmic spaces, space holds mysteries and potential, waiting patiently for us to continue exploring, questioning, and wondering about the deepest truths of existence. The emptiness we have contemplated tonight will continue long after human civilization has passed, long after our sun has exhausted its nuclear fuel, long after our galaxy has merged with neighboring systems, serving as eternal spaces of cosmic meditation, where the universe contemplates its own existence through the subtle interplay of forces that operate across unimaginable distances and timescales. Rest now, beneath the stars, as the silent universe stretches beyond time and space, knowing that you have journeyed tonight to the very edges of cosmic comprehension and touched the infinite emptiness that gives meaning and structure to all of existence. In your dreams, may you find the same profound peace that characterizes the cosmic voids, the same patient wisdom that emerges from contemplating vast scales of space and time, and the same gentle wonder that comes from recognizing your place within the magnificent architecture of a universe that includes both the densest concentrations of matter and energy and the most profound expressions of cosmic emptiness and silence.